I hope you can see the screen, right? So what is a generative model, right? So I'll quickly go over the, the overview, high-level overview of this generative model. Uh, is we have to sample the data. So uh, given some random inputs, say this is some Z. So if it is some random input of say sample from a Gaussian distribution, and this is the generative model. And so this is a model we are supposed to learn. So call it as f of theta, or let's call it as G, the generator, right? And this should output image X. So this is the whole the entire problem of the generative modeling. So basically, what do we do here? Typically, say we want to learn some distribution. Um, what was this? Okay, so we can finish by 5 if that's fine. Okay. Yeah, I'll try to finish things by 5. So basically, if you want to learn any distribution, so basically what we want to learn is the distribution of the data. So P data, that's called as P data of X, and we want to sample from this distribution. And typically, let's say we want to learn any distribution such as it's a normal distribution we want to learn. And so normal distribution is parameterized by mu mean and the variance sigma square, right? So typically, what we do is if we know the underlying distribution, since it is parameterized by mu and sigma square, we can empirically estimate the mean mu hat and sigma square hat, and we can then do a proxy distribution of data x1, x2, and so on xn. Right, x1, x2, and so on xn. Okay, so this is the entire problem of the generative modeling, and that is now let's say we are given the data sample from this normal distribution whose mean and variance is unknown. Now, as a function of data, you have estimated this mean and variance. And now we know that mean and variance we have estimated from the data. Now, and if you know that the distribution is normal, and then it's easy to now sample from this distribution. Now the key problem here is we don't know what is the underlying distribution of the images. It's not Gaussian, it's not any Laplacian or exponential, some standard distribution. It doesn't fit it, right? We don't know what it is. So this is the key problem in uh, estimating the distribution of the image kind of data, right? So what do we do in this approaches, right? So we typically go for estimating any distribution parameterized by say mean and variance in our toy example. Here we parameterized by a neural networks. Right? For a complicated distribution, we parameterize it by neural networks. Let's say this is what we want to estimate x1 and x2, p of x1, x2, and so on, xn, parameters by say theta. And since each of the data point is independent, we uh, this will factorize and so on for your function. Okay, so um, now what we do is we take the log. And this log of this is what we want to maximize this part, right? So log of the xi of theta. So this is the generic framework for any thing you want to fit to any distribution you want to fit to a data. So this is called as ML, maximum likelihood rule, right? So now, since we don't know what is the true distribution, so that we can fit the model to some parameters at theta, right? So what do we do in variational autoencoder is we assume that uh, there is some latent variable z, and that when we give it to some network called, you can call it as encoder. Okay, so now this should generate uh, um, the data basically. So this can be any known distribution such as normal 0 to I, and our aim is to fit a model called encoder, sorry, decoder, right? Decoder, and it should output a distribution. Let's say it's giving us some distribution of whose mean is let's call this as some f theta, right, f of theta, and let's say with some variance sigma square f theta. Let's put it here, and this is z. And this f theta of z should be of the size of the input. All right, so this is the encoder part. Now, what how we are obtaining z? Right, this is something called as uh, so this is decoder, and this is z. We want to encode the entire image x followed by say some network g, some neural network g. And this should go, and this should give us uh, a latent variable uh, z, and its distribution should be as close to as normal, with what we assume to be uh, so this is the entire the high level architecture of the autoencoders, and because of the probabilistic nature, this is a variational autoencoder. Typically we call it as a variational autoencoder. um, we can go on. If you want, I can derive the objective function which we maximize using in the variational autoencoder, or like, or we can go to GANs. I can give you the similar over high level overview, and we can solve problems. So what do you prefer? You want me to derive the objective function for the variational autoencoder? You can type in the whatever you want. Okay, so I'll similarly give the high-level overview of GANs. Maybe if time permits, we can come back and do the derivation for VAs in the end. Okay, so yeah, let me give a quick overview of GANs. So GANs are the other way of an alternate approach to do the generative modeling. So here, this objective function of GANs is like a game, some minimax game. So basically, we have something of a game, something like of this sort. Minimize over 3 addition of log of number of x. X is sampled as per p data plus function of z is p of z log of 1 minus d of q of z. Okay, so in GANs, there are two networks that one is supposed to learn. One is called as discriminator network, and another is a generator network. Right, so this is the discriminator. Say, call this is a discriminator network, and what we pass to the discriminator is when we pass the true image to p data, if an image that is sampled from p data of x, the true underlying distribution, which we don't know. So we assume the data set is given is generated from this p data, and we take that x and we give it to discriminator, call it as theta, and its output should be high, right? And when we sample the image, say called fake image, right? This fake image should come from another network called generator G. Let's say it is parameters by 5. This give and this should generate from the random inputs. Let's say I give some noise, and this should generate me an input, an image X fake. Right now, when I pass this input to the discriminator, it should give me a low value for this. But generator tries to it tunes X in such a way that it discriminator thinks this is coming from the real distribution, and it when generator is tuned, it makes the output of discriminator to be high. And when discriminator comes in, it makes the input, it makes the value high when it sees the true image. So these two works adversarially to each other. Right. So this is the high level overview of again how this thing works. So at equilibrium, right, this two, one is minimizing and one is maximizing. At equilibrium, generator should be able to achieve uh, data which discriminator gets confused, right? It should give half of probability. Like if x, it should not be able to distinguish the true data or fake data, right? So whatever it comes, it should say that it is fake with probability half, and if fake comes, it should say that it is the true data with probability half. It should get confused. So that's the goal, ultimate objective of the GANs. All right. So there are any questions on this? I can go on. Otherwise, we can go and solve the problem. Okay, so let's try to solve our problems here. I'll share the screen. Just give me a second. I hope you can see the screen, right? Yeah. Yeah, the first question is why do we even need to compute the evidence lower bound and why not the maximum likelihood directly, as I was explaining in the initial phase of our discussion? And assuming that xi is the input and z is the latent variable, and p of xi given z is the conditional distribution of xi given z, and p of z given xi is the posterior of z given xi. So which of the following is true? The data distribution is unknown, or the posterior is untractable, and the only one is true, or both one and two are true. So any guesses? Should be able to answer if you have seen the variational autoencoder derivation. Can take a minute and I'll explain. Yeah, so basically both the one and two are true because the data distribution itself is unknown. Because if we know that what is the data distribution, then would have directly fit a model. The distribution is known, and we can just fit the maximum likelihood to the parameters and then find the parameters and then sample it from distribution. Because it's unknown, and that is one of the problem. And typically, the distribution of latent uh, given x size untractable is because it to compute this we end up requiring to know this p of xi, which itself is unknown to start with, right? So both one and two are correct. So which of the following is the correct loss function for variational autoencoder? So the first term is the uh, maximizing the log probability of the image xi given uh, the latent z. And the second one is sort of scale divergence between the latent distribution and the underlying the distribution of the latent variable. I mean, the posterior of latent given xi and the underlying distribution of this. So, yeah, here again, if we know the derivation of variation autoencoder, we can quickly see that the first term is the correct. Okay. If time permits, we'll do. This is what I was planning to do in the initial part when I said right. If time permits, we will do. And yeah, I said option one is correct. Now, even having decomposed the loss function as a lower bound and try to maximize this lower bound with respect to parameters, this theta here and phi here, right? So what are the difficulties in optimizing using gradient descent and ascent with respect to parameters theta and phi while training the variational autoencoders? Right. So and what is the suggested solution if there are any difficulties? Right. So optimizing with the parameter theta with using gradient descent works well. This is in fact true because we can directly take the gradients with respect to theta under the expectation. And second option is optimizing phi is problematic as the gradient involves the expectation of the underlying distribution. Point is if we want to compute the gradient with respect to phi, and if we can see that we cannot take gradient with respect to phi inside the expectation because expectation itself is dependent on the phi, right? So we can't just take the gradients inside to the log and just do the processing. It doesn't work. And so to solve this problem, I think the authors have proposed something called as reparameterization technique. Right? So this is the reason all the above three reasons are in fact true. Okay. And again, what are the which of the following are true regarding the GAN training? Right. So the difficulty in training due to zero sum objective. Yes, that is true because uh, one is trying to maximize the objective and another is trying to minimize the objective, and it's very hard to attain equilibrium in such kind of training. Mode collapse, which is also true because the mode collapse refers to a situation where we uh, end up capturing only few of the classes. Let's say we want to generate a CIFAR 10 data set and it has 10 classes, and it can happen that training converges to a point where we only see 8 classes and 9 or 10 are missing. So such a scenario is typically referred to as mode collapse. And evaluation of generated images. So we have a this generators, right? Generative networks. So there's no clear way to evaluate how good these generated images are, right? And so only one and two are correct, and all one, two, three are correct. Why does all one, two, three are correct are incorrect? Okay. Now consider the following GAN objective as I have briefly gone through. And suppose the true generated distribution is known, right? It means we are not learning the generator. It's given we understood the generated distribution and it's given to us, and the underlying data distribution is also given to us. So if this is the scenario, what is it the discriminator is trying to look for, right? So this is simple, and here this is the objective function because the generator is given to us, and there's nothing with respect to generator we want to optimize, right? And this quantity is same as this thing. As expectation I've written it as integral, and this is PD is the true data distribution, and this is the log of discriminator of this x, and expectation with respect to uh, the generated distribution, which is also given to us to be known. And since g of z output is the to the it that data itself, right, generated, so that's why it is x here. and we want to maximize this quantity with respect to z. So thing is maximized if the the integrand inside this thing is maximized. So we can just maximize, differentiate this quantity with respect to d, and we see that the optimal discriminator in this sense will is nothing but the, the the true data distribution divided by the true data distribution plus the generated distribution. Okay, and I think this is the last question. And so, what are the typical measures that are proposed to evaluate the quality of generative models? So, inception scores, pressure inception scores, scale divergence, and reverse scale divergence. So, the correct options are 1 and 2, inception scores and pressure inception score. And KL divergence is the divergence measure that is used to um, quantify how different two distributions are. I mean, if we had known the underlying true generative true data distribution, then this using this thing makes sense. A reverse scale is same as the three, but the expectation is taken with respect to the other probability distribution. So again, reverse scale is again useful when we know the two distributions at hand, but we don't know. Right? So 1 and 2 are the correct answers. Yeah, so these are the questions for the day, and I will be able to answer if there are any other questions if you have. Otherwise, we can go ahead and do the derivation of the evidence lower bound of VAE. Yes, no. Okay, so let's try to do the this thing, the evidence lower bound thing. Right. So P of xi we can write as using Bayes rule, if you know, right? So what is Bayes rule? P of xi given z. P of z xi times P of z. This is P of xi times P of z given xi times P of z. Okay, so let's take the log on both the sides, or you can just get P of xi here. So it's P of xi given z times P of z P of xi. Let's take the log on both sides. Call this as P theta. plus log of p of z minus log of p of x. And notice that this is true for all of for any z. This is true, and so yeah, and we can take the expectation with respect to z, and we assume z is drawn from some other uh, distribution, say q of z given xi, right? Right? We can take that expectation under q given zi, q of z given xi. And the expectation q z given xi. And here there's no dependency on it should be what? P of x, P of z given x. Yeah, sorry, this is P of z given x. P of z given x. And minus expectation of q of z given x times log of P of z given x. Okay, so this is what we have so far. Expectation underscore q of z given xi log p of x is equal to what's that? Right, p fusion under q log p theta of psi z minus expectation of q log of p theta of z given xi and some expectation q log of p of z, p of z. Yeah. Um, so now let's add and subtract one term, expectation underscore q log of q of z given x minus expectation of q log of q of z given x. Okay, so can combine these two terms and can combine these two terms. Equation of Q of theta side and equation Q Z on x side by p theta z on x side. Here we are combining these two, and these two we can combine as well. Now, that's the equation of Q log of P of Z divided by Q of Z given x. Right, so this quantity is negative of the KL actually, right? This quantity. So this quantity we can write as minus expectation of Q log of Q of Z given xi by P of Z. And because this is again a KL divergence between Q and P, and this is positive, this is always positive. So this entire quantity is greater than or equal to the expectation of Q of log P theta of xi given Z minus this quantity. So this is called the elbow evidence zone. Right. So yeah, this is what I wanted to prove in the first section. Yeah. So I can answer if there are any further questions, or otherwise, I think this is all I had today for you. I can answer questions if there are any issues with. I mean, if you have anything on their derivation side. No. Okay then. So we can sync up next week, and yeah, I'll upload the video and slides to in the link in the sheet.